My name is Rose Silver, and I'm going to talk about differentially private medians and interior points for non-pathological data. This is joint work with Maryam Aliakbarpour, Thomas Steinke, and Jonathan Ullman. So to start, I want to tell you about a very simple problem called the interior point problem. This is just a simple statistical estimation problem. You're given a distribution P, and you want to return an interior point of P. An interior point of P is just any point Y between the inf of the support of P and the sup of the support of P. So in this picture, you can imagine that in gray, we have our probability distribution P. Then any point in the blue region would be an interior point of P, and any point in the red region would not be an interior point of P. So the interior point problem says, given n IID samples from P, x1 through xn, return any point Y that is an interior point of P. This problem is in fact trivial. In particular, if you give me just one sample xi, well, this sample is already an interior point of P, and so I can just return the sample and I've solved the interior point problem. But it turns out that this problem is a lot less trivial if we're concerned about the privacy of our samples. So consider the private interior point problem. Here, the setup is the same as before. We're given n IID samples from P, but now we want to privately return an interior point. Informally, what we mean by privately here is that we want that our algorithm does not leak information about our samples in its output. And so our algorithm from before would not be a solution to the private interior point problem. Now, more formally, what I mean by privately is we want a differentially private algorithm. And so whether or not you've seen the definition of differential privacy before, I want to just quickly define it so that we're all on the same page. I like to think of differential privacy with the following meme from The Office. This is Pam, and over here she's handing someone two pieces of paper and says, corporate needs you to find the differences between this picture and this picture. Pam then reveals behind the scenes that in fact they're the same picture. And so I think this is very similar to the definition of differential privacy. Consider these two pictures. On the left, we have a dataset D of data points x1 through xn. On the right, we have a dataset D prime that's a copy of D where we just change the value of one of the data points. So in algorithm A, if it is differentially private, then what this means is to an attacker, these two pictures look the same. In other words, if an attacker didn't know whether the algorithm was run on D or D prime, it can't use the algorithm or the output of the algorithm to figure that out. So more formally, an algorithm A is epsilon delta differentially private if for all pairs of neighboring datasets D and D prime that differ in this way, and for all events E in the output space of A, the probability that A of D is in E is very similar to the probability that A of D prime is in E. The similarity of these two probabilities is controlled by the parameters epsilon and delta. So that's differential privacy. And now let's return to our original problem. So earlier, we were interested in the question of, can we solve the interior point problem with privacy? And it turns out the answer to this question is a surprisingly negative one. In fact, at Fox 2015, Bun, Nissim, Stemmer, and Vadhan showed that any epsilon delta differentially private algorithm that solves the interior point problem must use at least log star of the domain size of our distribution. Now, this log star domain size might not seem like a big concern or a big negative result until we remember that the domain of P could be continuous, could be the reals. And in this case, log star of the domain would be infinite. So this result shows a surprisingly impossible result for solving the interior point problem with privacy. So this is genuinely bad news, as a lot of the statistical estimation problems that we're interested in are a lot of the times just refined versions of the interior point problem. And what this impossibility result has led to is a long line of work where researchers have tried to bypass the impossibility result by solving the interior point problem for restricted classes of distributions. In particular, prior work has shown that, for example, if you assume that P is Gaussian, the problem becomes tractable again. Also tractable when you assume that P comes from, or P has a probability density that's lower bounded within some fixed size interval around the median. And also when you assume that P has a smoothness property everywhere. So this is some past work, and it really kind of intuitively what it's saying is that it seems that the Bunn et al. Lower bound only applies to very unusual or pathological distributions. And so the goal of further research and the goal of our paper was to formalize this intuition with a very light distributional assumption. And so in this work, we introduce an assumption called C-bounded normalized variance. I'll define what this means in the next slide, but at a very high level, it's an assumption that's trying to capture a simple statistical property that is held in most natural or real-world distributions. And so what we show is that if your distribution has this C-bounded normalized variance property, then there is an epsilon delta dp algorithm that returns an interior point and uses only a small number of samples. So what is this C-bounded normalized variance property? And as a shorthand, we'll call a distribution with this property a C-bounded distribution for the rest of the talk. What this means is that this quantity and this quantity are within a constant factor of each other. The quantity on the left is just the standard deviation of our distribution, and the quantity on the right is the expected absolute deviation of the probability distribution. So what this means morally is that distributions with constant bounded normalized variance are those for which the standard deviation serves as a constant factor proxy for the expected absolute deviation, i.e., the expected amount by which the distribution deviates from its mean. In other words, a distribution is C-bounded if the standard deviation is a meaningful quantity of the distribution. So, not surprisingly, all distributions that we deal with day to day are C-bounded, and it's natural to think that probably most real-world distributions, including the messier ones that you encounter in reality, are C-bounded as well. So with that in mind, what we prove is that if your distribution is C-bounded, then finding a private interior point is actually a tractable problem. Okay, so at a very high level, how does our algorithm work? The algorithm actually follows a paradigm that's pretty common for differentially private algorithms. Our first step is that we're going to break the number line into bins, and we're going to place our samples into bins based on where they land on the number line. So we're going to build a histogram of where our samples lie. And importantly, we want to use a bin width That's approximately the expected absolute deviation of our distribution. So you might say, how do we even get that bin width? And that, as it turns out, is step 0 of the algorithm, which is that we actually use a separate algorithm to approximate what the bin width should be. In fact, step 0, as it turns out, also makes use of the C-bounded property, but I'm just going to sweep this under the rug for the purposes of this talk. Okay, so this is step 1. You break the number line into bins whose widths are approximately your expected absolute deviation from the mean, and then you just build a histogram of where your samples went. Okay, step 2 is that we want to add privacy to these bins. And so what we do is we add truncated Laplacian noise to the counter in each bin. So each bin receives a random amount of noise, and this is what is going to ensure differential privacy. Okay, now for step 3, we're going to find 2 bins with sufficiently large loads, and we're going to just return as the output of our algorithm any point that lies between these 2 bins. So intuitively, because these bins have very large loads, those very large loads are caused by, cannot be caused by the random noise. They're probably caused by actual samples, and so we can be confident that any point between those 2 bins should genuinely be an interior point. Now, we can't afford to just return any point within those bins because we don't know exactly where within any one bin which points are interior points. So it's critical that we find 2 disjoint bins and return a point between them, and that lets us find an interior point using our differentially private histogram. Okay, so at this point, we need to address some possible failure modes of our algorithm. So problem 1 is well, what if we don't even have any large bins, right? Like our samples could conceivably be so spread out that we don't even get any bins above this dotted line. So here's one place where C-boundedness helps. C-boundedness actually tells us that Chebyshev's inequality is a meaningful inequality here for a distribution. It lets us conclude that a large fraction of the mass should be within a constant number of standard deviations, which is also a constant number of bins by C-boundedness. And so what that means is that there should certainly be at least one large bin. Okay, so actually the second problem is almost exactly the opposite issue. That is, what happens if our samples are too concentrated? So there's actually only one very large bin. And here C-boundedness helps in a more subtle way. C-boundedness tells us that our standard deviation isn't being determined by outliers, or at least that's one way to think about C-boundedness. So suppose that our points are in fact very concentrated in one bin. Then it must be the case that our standard deviation is actually smaller than the size of the bin. But we can now use this to conclude that actually that means our bin size was wrong, because our bin size was supposed to be an approximation of the absolute expected deviation, which should be smaller than the standard deviation by C-boundedness, and so we arrive at a contradiction. And so it's kind of an interesting circular path to a contradiction, but here again, the high-level point is that C-boundedness helps us dodge this problem entirely. So that's the very high-level idea of what's going on with our result. That's how C-boundedness lets us actually get a problem that bypasses the Banach lower bound and returns an interior point using only a small number of samples while also preserving privacy. And what I want to do in the last few minutes of the talk is tell you a little bit about the other main result of our paper, which is for privately approximating medians. So the private alpha approximate median problem is the same setup as before. You're given n IID samples from a distribution, and now you want to return a point that's not just an interior point, but a point that's within plus or minus alpha quantiles of the median. So this point should be a good approximation of the median for this probability distribution. And so what we do in our second result is we add this new result about approximate medians. It turns out that C-boundedness is provably not sufficient for the approximate median problem. That is, for all private algorithms, there exist C-bounded distributions that run the sample complexity up to infinity. But if you assume C-bounded normalized variance on the conditional probability in that region around the median, so the region within plus or minus alpha of the median, then that is enough, even without knowing what that region is a priori. And so under that assumption, the assumption that you have C-boundedness kind of around the median, you can actually solve the alpha approximate median problem with differential privacy and with a small number of samples. So those are the two big results of the paper. And if there's one takeaway from this talk, maybe it should be that one of the things that's neat about differential privacy is it takes problems that are normally so simple they might even be considered trivial, and it turns them into challenging and impossible problems. And so the goal of this paper is that we wanted a single framework for formalizing the intuition that, at least in this case, the impossibility results were only for pathological distributions. And so our main contribution was algorithms for these problems that formalize that intuition. Thank you.